Okay, so today's lesson is on the fundamental theorem of algebra. And the fundamental theorem of algebra basically says that the degree of a polynomial tells you how many solutions that polynomial will have. That's it in a nutshell. So for this first row of the table, you see that we have a linear equation with a degree of 1, and the number of solutions to that equation would only be 1/2, which is just one solution. Here we have a quadratic equation, so the degree is 2, and when you solve that equation, you end up getting 2 solutions, positive square root 2 and negative square root 2. Then we have a cubic equation with degree 3, and you see that we have 1 solution, 2 solutions, and 3 solutions. Excuse me. So the degree of the polynomial tells you the number of solutions that there will be. Last example, you have a cubic again, and you still have 3 solutions. It just so happens that one of them repeats twice. So you count repeated solutions separately. So that's what the fundamental theorem of algebra is. It's that the degree of a polynomial, the equation has exactly that many solutions. Okay, so let's just go straight into it. This lesson is very similar to the previous one in the sense that we're just going to be solving polynomial equations. Okay, so here it says how many solutions does this equation have? Well, since the degree is 4, we should expect to get 4 solutions. The degree is 4, so 4 solutions. Okay, now let's find those solutions. When it comes to solving polynomials, you always want to try to factor first, and when that doesn't work, then you can try the rational root theorem. So for here, if I look at this, there's 4 terms, so I'm going to factor by grouping, because it looks like it'll work out. So I'm going to take out an x cubed, so you have x plus 1. Take out an 8, so you have x plus 1. And then that's what you have. Now, I know that this part can't be factored further, but if you look here, that's the difference of cubes, so that can be factored further. If you remember, when we factor cubes, you want to identify your a and your b value. So in this case, my a value is x, and my b value is 2. So then, if I just follow the formula, this will factor to x plus 2 times x squared minus 2x plus 4 times x plus 1. And if you remember, in the lesson that we learned this, I had mentioned that whenever you factor with the cubes, this part here won't be factored further, okay? So at this point, this is as factored as this polynomial is going to get. So now I'm going to take this and set each factor equal to 0. Sorry. So that means we have x plus 2 equals 0, x squared minus 2x plus 4 equals 0, and x plus 1 equals 0. Now, the first and the last one are easy. That's just negative 2. That's just negative 1. What do I do here? Well, just because it's not factorable doesn't mean I can't do anything with it. I can look at this as a quadratic equation, and I can try solving it using some of our other methods. So you could do completing the square in this one since the b value is even, or you could do quadratic formula. Now, last class we had done the quadratic formula, so let's complete the square for this. If you remember, completing the square, I do b divided by 2 squared. So in this case, that's negative 2 divided by 2 squared, which is going to give me a positive 1. So I have x squared minus 2x plus 1 minus 1 plus 4 equals 0. Then I factor the perfect square trinomial, and I get x minus 1 squared, and then I'm going to have plus 3 equals 0. So now I'm just going to solve this by isolating x. And because there's a negative under the radical, this is going to become I root 3. Okay? So my 4 solutions to this equation that I'm going to get are -2, -1, 1 plus I root 3, and 1 minus I root 3. So those are the 4 solutions that I would get. And remember, you don't have to write it out, or I shouldn't say remember. This is the first time I'm telling you. You don't have to write it out. You don't have to write it out, like this, but I'm writing it out in that way just so that you guys realize like there are 4 solutions and so that you can see them clearly. Okay, let's move on. So here we have another problem where we want to find the zeros. Essentially just means find the solutions or the x-intercepts, right? Now for this particular problem, none of my factoring methods, my traditional factoring methods, are going to work because I have more than 4 terms. So here's where I need to use the rational root theorem. So remember, that's P over Q. It's the factors of the constant term, so in this case, factors of 8, over factors of the leading coefficient, which in that case is just 1. Okay, so remember we always look at both positive and negative values. So the factors of 8 are 1, 2, 4, and 8. Factors of 1 are just 1. So now all the possibilities, well, 1 divided by 1 is just 1. 2 divided by 1 is just 2. So on and so forth. So those are the possible, remember these are the possible solutions. But if I want to find out which ones are the actual solutions, I have to test them using synthetic division. So that's what I'm going to do now. I always start with the smaller numbers just because it's easier and they actually usually end up being the ones that are the factors. So I'm going to start with a positive 1 and let's just see if it works. So 1, remember it's 5, 3, 2, 1, none. So that means I need a placeholder here of plus 0x to the 4th. So that's 1, 0, 1, -2, -12, -8. 5, 4, 3, 2, 1, none. Okay. Bring down the 1, multiply, add, and this is not going to work. Okay, I can already tell it's not going to work. So what I do is I usually leave most of what I wrote there, and now I just try -1. And that ends up working. So because that 0 is our remainder, we know that -1 is a solution, which means x plus 1 is a factor, okay? So I'm going to take my original function, f of x, and now I can write it as the product of the thing I divided by, which in this case is x plus 1, times the quotient, which is represented by sum of that. So the quotient is going to be x to the 4th minus x cubed plus 2x squared minus 4x minus 8. If you notice here, this part can't be factored further using traditional methods, so I still have to do the rational root theorem. And this is as factored as it gets. So I'm just going to test more values. I already tested positive and -1, so now let's test positive 2. And I don't want to test it with the original function. I want to test it with the part that still needs to be factored further. So 1, -1, 2, -4, -8, 4, 3, 2, 1, none. Okay. Just going to make that a little bit smaller. Not too small. Okay, so bring down the 1, 2, 1, 2, 4, 8, 4, 8. Oh, look at that, it works. Very nice. Okay, so because that worked out, now that I know that f of x is equal to the x plus 1 still there, and now this, what I'm about to write, is the factor form of what I just underlined. So it would be x minus 2 times x cubed plus x squared plus 4x plus 4. And now if you look at this part, that can be factored using our traditional methods. So I'm going to do factor by grouping. So x squared times x plus 1 plus 4 times x plus 1. And then we have x squared plus 4 times x plus 1. And let's not forget that we still had the x plus 1 and the x minus 2 in front here. Okay. Now remember, the whole point of this was to find the zeros. So at this point, now that I have it factored as far as I could go, because remember, we cannot factor this further since it has a plus sign, I'm going to set this equal to 0, and each piece will be equal to 0. I'm just going to copy and paste that. Ta-da! So now I just set each piece equal to 0. And it does end up that one of our solutions repeats. We get a repeated solution of -1. Here, remember, we have to isolate. So that's going to be plus or minus 2i. Okay, so the degree of this polynomial was 5, and we do get 5 solutions. It just happens that one of them repeats twice, right? Our solutions are -1, positive 2, another -1, positive 2i, and negative 2i. Okay? And again, you don't have to write it like this. I'm only doing that so that you guys can start to see how there are, in fact, 5 solutions. Okay, moving on. I'm sorry for the coughing. This example is very similar to one we did last class. Just like we saw here in this example, if you get a complex 0, 0 that has an I, that will always come in a pair. It'll always be the positive and the negative. Just like in the last lesson, we saw that if we had an irrational 0, like 2 plus radical 5, that would also come in a pair, 2 minus radical 5, because it's always from problems where we have to use the quadratic formula or we have to square root both sides, and so it gives us that plus or minus answer. So these will always come in pairs, okay? So all that means is, if now I give you a problem where you don't know the polynomial function but you know the zeros, in this case the zeros are 2 and 3 plus I, how do you find the polynomial? And the key, or at least the key to starting the problem, is to recognize that if I have a 0 of 3 plus I know for a fact I also had a 0 of 3 minus I, because remember, they're going to come in a pair, okay? They are what we call complex conjugates of each other, where they're basically the same number, but just different signs. Or sorry, the same expression, but just different signs. So if I want to write the polynomial that represents this particular function, right? A 0 of 2 means I have a factor of x minus 2. And a 0 of 3 plus I means I have a 0 of 3 of a factor, of x minus 3 plus I, and of x minus 3 minus I. Now there's many different ways that you could do this problem. I'm going to show you the easiest way, okay? We're going to start by tackling the most complicated part, which is the last 2 parentheses. Now the first thing that you want to do is you want to distribute the negative, and then you want to regroup. And for the regrouping part, maybe use a different color, okay? So all I'm going to do is distribute the negative, so x minus 3 minus I, x minus 3 plus I, and I'm going to regroup those 2 terms. So instead of having the 3 and the I grouped together, now I have x. Now I have x and 3 grouped together. And the reason why I want to do this is because now, looking at these 2 parentheses, they're basically the same thing except opposite signs. So what I have is conjugates. And anytime I have conjugates, if you remember from previous lessons, I'm basically going to FOIL, but I don't need to do the outer and inner terms. I only have to do the first and the last terms. And I'm going to treat my x minus 3's as my first terms and my i's as my last terms. So it makes this whole process so much easier. So here's what that looks like. If I treat this and this as the first term of both parentheses, then when I do first a FOIL, I get x minus 3 times x minus 3. And if I treat this and this as my last terms, I get negative I squared. Okay? Right? Let's keep going and simplifying this. So x minus 3 times x minus 3 is x squared minus 6x plus 9. And then I squared, if you remember from previous lessons, that's negative 1. But I still have that negative, so this is going to become a positive 1. And then combining those like terms, you get plus 10. Okay, now let's not forget we had x minus 2 here. So the last step will be to multiply x minus 2 times x squared minus 6x plus 10. So I'm just going to distribute this. It's not foiling, I'm just distributing it. Okay, so if I distribute x squared in, I get x cubed minus 6x squared plus 10x. And then if I distribute the negative 2 in, I'm going to get negative 2x squared plus 6x minus 20. Combining my like terms, that's what you should get. All right, so hopefully not too bad. This next part of the lesson is something that we haven't seen before. It's a little bit different, but it's not too bad, and it just takes a couple practice problems before you get the hang of it. Okay, so there is a famous mathematician, Rene Descartes, who has come up with a bunch of different theorems, a bunch of important things that are good for us to know. I knew it. Hold on one second. What did I do? Oh, this should be 12. That's my mistake. Sorry. I had a feeling I made a mistake in there somewhere. And so this should be 22x. Sorry about that. Okay. Going back to it. So, one of the things that he came up with, or didn't come up with, I should say discovered, is the fact that you can figure out how many positive real zeros, how many negative real zeros a particular polynomial function has just by looking at the way in which the signs change. The best way to understand this is with an example, okay? So, to find the number of positive real zeros, all you want to do is look at the number of changes in the signs of each term, or this number subtracted by 2. Okay, what does that mean? Let's just look at this example down here. So, if you notice, we have the first term is positive, the second term is negative. So that's one sign change. We went from positive to negative. The next term is positive, so that means that's another change from negative to positive. Okay? Then positive to negative, so that's another change. And then the signs don't change again because the rest of them are all negative. So that means for the number of positive real zeros, we could have 3, or just keep subtracting by 2 until you can't anymore. We could have 3 or 1 in this case, okay? Because of the fact that if I was to keep subtracting, I would end up getting a negative number, and you can't have negative amounts of positive real zeros, okay? So that's the first thing. You look at f of x, how many times does the sign change, and then you keep subtracting that value by 2 until you can't anymore. Then for the negative real zeros, it's basically the same thing, except instead of looking at the original function, you're looking at f of negative x, okay? So the first thing you have to do is you have to figure out what f of negative x is. How do we do that? You plug negative x into the function. So negative x to the 6 minus 2 times negative x to the 5th plus 3 times negative x to the 4th minus 10 times negative x to the 3rd minus 6 times negative x squared minus 8 times negative x minus 8. Now, the easy way to approach this is that anytime you have negative x raised to an even power, it's going to become positive. So this will simplify just to positive x to the 6th. This, or I should say this part, is going to simplify to positive x to the 4th, which if you multiply that by a positive 3 is just positive 3x to the 4th. Here, that simplifies to a positive x squared, but then you have that negative 6, so that's a negative 6x squared, okay? Anytime you have a negative x raised to an odd power, that's going to stay negative. So this is going to be negative x to the 5th times negative 2, so that becomes positive 2x to the 5th. Negative x cubed times negative 10, positive 10x cubed. Positive 8x, negative 8. Okay, so how many times does the sign change here? Positive to positive, no change. Positive to positive, no change. Positive to positive, no change. Positive to negative, 1 change. Negative to positive, another change. Positive to negative, 3 changes. So, what that means is we have a similar scenario to the positive real zeros. So for negative real zeros, there could be 3 or 1. Okay, so now this is how we take our findings and we organize it in a way to figure out what the possibilities are for this function. Now here are the possibilities. We could have positive real zeros. We could have negative real zeros. We could have imaginary zeros. And then we have the total number of zeros. Okay? And now we're just creating cases. So what are the cases? Well, I could have 3 positive real matched up with 3 negative real, which means I would have no imaginary solutions because I know that I need to get a total of 6 solutions since that's the degree. So this is one possibility. This is one case. Are there any other cases? Well, yes. The case where I have 3 positive real zeros, but only 1 negative real zero. In this case, I need to have 2 imaginary so that I get my total of 6. Any other cases? Okay, well, now let's look at 1. What if I only have 1 positive real zero? I could have 3 negative real zero, which means I need 2 imaginary to get my total of 6. Or I could have 1 real and 1 negative, which means I need 4 imaginary to get my total of 6. So this here is our final answer. And if I was to go and look at the zeros of this particular function, one of these would have to be true. I'm not sure which one, but one of them has to be true. Okay, and that's it. So I hope this helps.